Greetings everybody, this is Dr. Gomez. This video is going to cover the part 1 of the Chapter 9 Lecture Notes, and I might break this video up into 2 or more videos, again just to keep the size manageable. But this deals with statics and torque. And now with Chapter 9 and then Chapter 10, we're now moving from linear motion to rotational motion. So we want to now set our minds to be thinking in terms of rotational motion as opposed to linear motion. Well, first let's look at what is a torque. I'm sure you've all heard of, for example, a torque wrench. Well, what is a torque? A torque occurs when an applied force, we'll call F, when an applied force acting on an object causes the rotational motion of the object to change. So in other words, it's a force that produces a rotation. When you apply a force to the object rotates. And typically it rotates about a pivot or a rotation axis. The terms pivot and rotation axis are used interchangeably. Do not get confused. They mean the exact same thing. And now the symbol for torque is the Greek letter tau. As you know, mathematicians and physicists love the Greek alphabet. And the equation for torque, the magnitude is given by the torque, tau is equal to Rf sine theta. Well, what is F? F is the applied force. Now R is what's called the lever arm. It is the distance from from the object where the force is applied to the rotation axis. R is simply the distance from F to the rotation axis. And theta is the angle between R and F. And the SI, the MKS, remember the term SI, MKS mean the exact same thing. The SI unit of torque is a Newton meter. Well, let's look at what this means. We won't worry about any numbers just yet. Here's an overhead shot of a revolving door. And the door is pivoted to rotate about an axis indicated by this black dot right in the center. Okay, so that's our pivot, or that is our rotation axis. Then we have 2 people pushing on this door. The girl is on one side of the door, applying a force we'll call F1. This person on the other side of the door, they're applying a force called F2. And notice these 2 forces will cause the revolving door to rotate counterclockwise, as indicated by the blue arrow. When the girl applies F1 and the man applies F2, that's going to cause the revolving door to rotate about that pivot, that black dot right in the center. That door is going to rotate counterclockwise. Now, let me zoom in a little bit. Hold on. Now notice this is the direction of F1, okay? And R1 is the distance from F1 to the pivot, to the rotation axis. Notice in this case, R1 and F1 are perpendicular. But R1 is the lever arm for F1. Notice, let's look at F2. This is F2, that's the direction of F2. Here is R2, direction of R2. Notice F2 and R2 are perpendicular. So in both cases, theta is 90 degrees. And you all know the sine of 90 degrees is 1. So tau 1, the torque produced by F1, is R1 F1. Tau 2, the torque produced by F2, tau 2 is equal to F2 R2, because in both cases the force and the lever arm, the angle between them is 90 degrees. Now that won't always be the case, but that's for that particular example. And remember, the sine of 90 is 1. So here, tau 1 is R1 F1 sine 90, which gives you R1 F1. Tau 2, R2 F2 sine 90 gives you R2 F2. Now, how do we know if a torque is positive or negative? Well, by definition, if a torque produces a counterclockwise rotation, as indicated by this arrow, it's very clear to see the door is going to rotate Counterclockwise. By definition, counterclockwise is a positive torque. So in this case, tau 1 and tau 2 are both positive. Well, let's look at another example. Here we have, in panel A, we have these kids on a little playground ride. You know, it's not really a merry-go-round, but they get on this thing, and it's pivoted to rotate about an axis right through the center. And typically, you know, an adult or another kid, you know, pushes on this little merry-go-round type ride, and the kids move in a circle, and they have a lot of fun. Well, notice in this case, this person here, if they're exerting, they grab, you know, a handle on the ride, and now notice if he exerts a force as indicated in this direction. Well, remember, he's at the edge of that little merry-go-round type ride. That's the force. R is the distance from where the force is applied, the edge of this disc, if you want to call it. R is the distance from the force to the rotation axis, right there at the center. Well, notice in this case, they are parallel. In other words, the force is applied along the line of the lever arm. Well, in that case, the angle is 180 degrees, and sine of 180 is 0. So that produces, excuse me, not 180, I misspoke. The angle is 0 because F and R are parallel. 180 is anti-parallel, not that it matters, sine of 1, but in this case, the angle between F and R is 0. And the sine of 0 is 0. And we call that a radial force. Any force that is directed along the lever arm, i.e. in the same direction of the lever arm, that the angle is 0, and that's 0 torque. Now suppose instead he's producing a force at the same handle, but now suppose he produces a force indicated by this red arrow F. Well, when he pulls on the handle, if you will, if he pulls on with that force F, it's going to cause the ride to rotate clockwise. And now the angle theta, the angle between, that's the angle between F and R. Well, that angle is theta. And the component of F that is perpendicular to the lever arm is F sine theta. So this torque is R F sine theta. And in this case, the torque is negative because it produces a clockwise rotation. But this is the case where the torque is tau is equal to RF sine theta. So the torque in panel B is RF sine theta, and it's negative. Now let's look at another example. Let's look at the net torque on a cylinder. And again, you sort of want to think a little bit outside the box, because typically when we talk about torques, the object is going to be fixed to rotate about a certain pivot, about a certain axis. And in this case, we have a one-piece cylinder, but it has a core section of radius R2 and an outer radius of R1. And it's pivoted to rotate about a central z-axis, indicated by this solid line going right through the center, and dotted line passing right through the geometric center of that cylinder and there. So it's pivoted to rotate about a central z-axis. And you're applying, there are two forces, two ropes are wrapped around the cylinder, and somehow you pull on the ropes. And remember, string, rope, cable attached to an object, that's a tension force. Okay? So one of the ropes, the tension force is T1, as indicated by the arrow. R1 is the lever arm. That's the distance from T1 to the rotation axis. Remember, the rotation axis is indicated by this line, the central z-axis. So T1 and R1. And notice, what is the angle between them? 90 degrees. Now let's look at the second rope. Well, the tension is T2, and the lever arm is R2. Remember, by definition, the lever arm is the distance from where the force is applied to the rotation axis. Notice again, but the angle between T2 and R2 is 90. Sine 90 is 1. We don't need to reinvent the wheel. And remember, the cylinder is free to rotate about the central z-axis. Well, T1, excuse me, tau 1, which is R1 T1, tau 2 is R2 T2. Remember, in general, tau is RF sine theta. But in this cylinder example, theta is 90 degrees. Sine of 90 is 1. That won't always be the case, but you want to get used to it. So now tau 1, which is R1 T1, that's a negative torque because it produces, as indicated by this arrow, it produces a clockwise rotation. Now, tau 2, which is R2 T2, tau 2 is positive because it produces a counterclockwise rotation, as indicated, again, by the respective arrows. So the net torque is simply the sum of all the torques. In this case, there's two of them. R2 T2 is positive, R1 T1 is negative, hence the negative sign there. So the net torque, or total torque, is R2 T2 minus R1 T1. Now, the weight of an object can also exert a torque. And how so? Well, let's look at this example. So suppose we have a uniform rod, meaning again the mass is distributed uniformly, so we know that the center of mass of the rod is actually at its geometrical center. So that's where the weight of the rod will act. And let's suppose that this rod is pivoted about one end. So it's free to rotate. That's our rotation axis. That's the pivot. It rotates about that pivot. And we're going to assume that the pivot is frictionless. That won't always be the case, but again, we're starting with the simple examples and we'll get more advanced. Well, when you release the rod from rest, what happens? The weight of the rod, which we know acts at its geometrical center, that's the whole idea of center of mass. Why do we care about the cm? And usually I refer to center of mass as cm, because any forces acting on the object, they act at the cm. The object behaves as if all the forces acting on it act at the cm. Well, the cm, because it's a uniform rod, the cm is right at the geometrical center. That's where the weight acts. mg is pulling down. Now the distance, the lever arm, the distance from mg to the pivot, to the rotation axis, well, that distance is L over 2. I wanted to make this figure a little bit better. So mg, that's the way, in other words, the rod is released from rest. It's got this frictionless pivot at one end. So when it's released from rest, the weight, mg, will cause the rod to rotate. I want to know, I don't really care if it's positive or negative, I want the magnitude of the net torque. Well, the force is mg, the lever arm, the distance from the force to the pivot, well, that distance is L over 2. Because the rod has a length of L. And the angle between them clearly is 90 degrees. And so the sum of the torques, of which there's only the one, the force is mg, and the lever arm is L over 2. So the torque, the net torque, we want the magnitude, I don't care if it's positive or negative, the magnitude of that net torque is mg L over 2. Let me check the time. Okay, 14 minutes. I'll do one more example. Let's look at the net torque acting on a door. And here again, this is a top view of a door. Here's the hinge. Here's the hinge here, and this is the door. The door has a total length, and we're going to assume again that the door is uniform. I don't know that that really matters in this problem, but the door is a width of 2 meters, so that's the distance from the hinge to the other end. That distance is 2 meters. Two forces are applied to the door as indicated in the figure. There's the 10 Newton force acting at the opposite end of the door from the hinge. It acts at an angle of 60 degrees. Then there's 10 Newton force acting right at the center of the door, and it acts at an angle of 120 degrees with the door. And I want to know what is the net torque. And when we say with respect to the hinge, meaning, the hinge, in other words, the left right there, this is like a top view of a door. And so it rotates about, you all know a door rotates about the hinges. That's why, well, so the 10 Newton force acting at the middle of the door is going to produce a positive torque, because what's going to happen, is that when you pull, remember, the door is fixed to rotate about the hinge. So when you pull on it with this force, it's going to cause the door to rotate counterclockwise. That's a positive torque. Now let's look at the 10 Newton force acting at the right end of the door. In other words, at 2 meters from the hinge. Well, you're pulling down on the door like that, it's going to rotate clockwise. Again, it might take some getting used to. So the 10 force acting in the middle, that's the positive torque. The 10 Newton force acting at the right end, that's a negative torque. And remember, torque is RF sine theta. Well, let's do the positive torque, the one in the middle. The force is 10 newtons. Okay, the force is, and we know, again, we're looking, this is the positive torque. So in our sum, I'm going to start with that one. Well, the force is 10 newtons. The lever arm is 1 meter, because that 10 Newton force is it's 1 meter from the pivot. So that's my R is 1 meter. The force is 10 newtons. And the angle between the force and the lever arm, the angle between F and R, that angle is the 120 degrees. So that's RF. So this is R F sine theta. And that torque is positive. Now let's look at the negative torque, the torque produced by the 10 Newton force acting at the right end of the door. Well, we know that torque is negative. Okay, there's my minus sign. We know the lever arm is 2 meters because the door is 2 meters wide, so this force is 2 meters from the pivot. Okay, so it's minus. That's my R. The F is 10 newtons, and from the figure, the angle between F and R is the 60 degrees. And if you plug in the numbers, you get a net torque of minus 8.66 Newton meters. Now very important are what we call static equilibrium problems. I'm going to save that for the next video. Again, I want to keep the size relatively manageable. So I'm going to stop here with net torque. Let me go ahead and save this video and get it posted.